Okay, so hello guys. So I'm Yashasvi Bhattacharya and today we'll be learning about an important reaction which is known as esterification reaction. Now this reaction is present in both 10th syllabus and in 12th syllabus. Although the mechanism of this reaction is in the 12th standard, but it is important to know the mechanism of this reaction which will help us to understand its products and reactants a little bit better. But before we actually dive into this mechanism of this esterification reaction, we need to understand some terms known as nucleophiles and electronegativity. So the term nucleophile and electronegativity, originally as per the CBSE syllabus, both of these two terms are present in the 11th standard, but we need to understand or at least know about them before we can dive into the mechanism of this esterification reaction. So without the further delay, let's start with the term nucleophiles. Now what does this term mean? Well, to put it in simple words, nucleophiles, or simply put only nucleophile, means a species. Now when I say a species, it can be an ion or a neutral molecule. Now a species which wants nucleus. Now obviously it will not be able to get a nucleus as it is. So what we are trying to imply by this word nucleus here is this specific species will actually want some either positively charged, fully positively charged, or partially positively charged center of a molecule. Now when I say positively charged, that simply means that species can have or it wants a cation. So by default, if a species wants a cation, then that specific species must be an anion. So that means all the anions will be classified as a nucleophile. So some examples of these nucleophiles can be OH minus hydroxyl ion, or fluoride ion, iodide ion, or sulfate ion. So all of these will actually come under the classification of nucleophile. Why? Because all of them are anions, all of them are carrying a negative charge, and hence to neutralize that negative charge, all of them want a positive charge, or in other words, a nucleus. So by that reasoning, we can classify all these anions as nucleophiles. Now what is the case with partially positively charged species? Now see, in order to understand this partially positively charged center, we need to understand the concept of electronegativity. In short, EN. So what does this term actually mean? So electronegativity in its simplest form means the tendency, let me just write it. So in its simplest form, the electronegativity term means the tendency to attract the electron pairs. Most often they are bond pairs. Towards itself. Now how can that happen, or what are the examples of that? So let's take the example of oxygen. Now we all know oxygen and fluorine. We are familiar with these two specific atoms. So let's say we have a compound where oxygen is bonded with, let's say, carbon. So let's take the example of methanol, which is CH3OH. So if I write the structure of methanol, I will have to write or draw something like this. Now here we have the structure of methanol. Now notice here carbon is actually bonded with oxygen. Now oxygen is actually the second most electronegative element. First one is obviously fluorine. That's why I have taken the example of fluorine here. So the second most electronegative element is actually oxygen. Meaning the tendency of oxygen to attract the bond pairs towards itself is second only to fluorine. Now what it actually means in this case? In this case, let's focus on the covalent bond of carbon and oxygen. So if I can just focus on that specific bonding, then we will know that this specific bonding is formed by the sharing of electrons in between carbon and oxygen atoms. Now these two, we term them as bond pairs. Now ideally they should stay in between the carbon nucleus and oxygen nucleus. But as oxygen has a tendency to attract the bond pairs towards itself, so what will actually happen is, instead of staying, let's say here, the bond pairs will actually be moved towards oxygen. So let's say they stay here. Now why does it affect us? See, ideally the electron or electrons should stay in between the centers or the nucleus of carbon and oxygen. But as we can see here that the bond pairs of carbon and oxygen are staying more towards the oxygen. So that means the distance from the carbon nucleus to its electron in the bond is more than that of the oxygen and its electron. So that means a partially positive charge will develop on carbon. Now, as the electron is a little bit farther away from the center of the carbon or from the nucleus of the carbon, so that means carbon atom will feel a partial positive charge, which we represent by this sign. Now this specific sign is known as delta. Now why we are saying only partial? Well, we are saying it as partial because in this specific bond carbon does not have a full positive charge yet, and yet it is not like it's having a completely neutral electronic atmosphere around its nucleus. So there is a shortage of electron density around carbon's nucleus, but that is not fully developed. So hence, because of this reason, we actually term this type of cases as partial positive charges. So now I hope you guys are clear with the terms nucleophiles and electronegativity. So if those things are clear, so then let's actually start to understand how the reaction mechanism of esterification works. So in the case of esterification, we have primarily two reactants, namely one is an carboxylic acid, which has a general representation of this RCOOH, and another one is an alcohol, which has a general representation of R prime OH. Now this R and R prime, both of these two represent an alkyl group, but the point is that the alkyl groups of these two different molecules may be same or may not be same. Apart from that, we can also have aryl groups. Now what are aryl groups? Simply put, a benzene ring or a benzene substituent. So this esterification reaction actually works for both the alkyl groups and aryl groups, meaning this esterification reaction will be applicable to both the alkyl carboxylic acid and aryl carboxylic acid along with an alkyl alcohol or an aryl alcohol like phenol. So as this has a widespread application, so from that point of view I am going to restrict myself only to generalized terms. Once we understand the reaction mechanism, then I will come to some specific terms. Okay, so let's start with the reaction mechanism. So many of you may think that if we just mix an carboxylic acid and an alcohol, we will get the reaction done, but that is not quite true. Instead, what actually happens is we need to have an acid. To be specific, a mineral acid, let's say sulfuric acid or HCl, in trace amounts to actually catalyze this reaction. Now why we need to catalyze this reaction? Because this reaction is a reversible one. Reversible means? A reversible reaction means that the reactants can obviously react together to give us the products, but the products also can react in between themselves to give back the reactants. So as we are doing a reaction here, so obviously we will want the product and not the reactants back, because we already have those reactants at our hand. So in order to prevent the backward reaction, means the production of reactants from the products, we actually need to catalyze this reaction in a forward direction. So in order to do so, we need some sort of catalyst which role is played by sulfuric acid or HCl in this specific case. So let's now look at the actual mechanism. So at the beginning of this reaction, what happens is the H plus produced by the sulfuric acid or hydrochloric acid actually attacks this oxygen atom. Now why specifically this oxygen atom and why not this one? Because look, here we have a double bond in between carbon and oxygen, means the electron density is more in this area than in this case. So as a result of that, what happens is the hydrogen cation H plus directly attacks the carbonyl oxygen, meaning this oxygen, and forms a cation like this. Now many of you will notice that I have placed a positive sign on top of oxygen. Why I have placed a positive sign on top of oxygen? Because oxygen at max can form two bonds, but here it is bonded with hydrogen and at the same time it has formed two bonds with carbon. So that makes total 3 bonds for oxygen. Now as this specific oxygen has formed 3 bonds, then that means it is deficient of electrons. So for that reason I have placed a positive charge on top of oxygen. And as we learned a little bit earlier, oxygen is the second most electronegative element. So that means oxygen will not like this scenario, and hence to release this carbonyl oxygen from this scenario, an alcohol molecule attacks the carbonyl carbon, meaning this specific carbon from its oxygen end, which actually releases the one of the double bonds of the carbonyl group, and as a result we get something like this. But see, again another oxygen atom is carrying a positive charge. So obviously this specific scenario is also not suitable. So obviously this specific oxygen atom will try to get rid of this hydrogen atom. Why hydrogen atom and why not this alkyl group here? Because carbon oxygen bond is much more stable than oxygen hydrogen bond. So it is easier for this oxygen to release one H plus rather than to break this carbon oxygen bond. So in this specific scenario, what happens is there happens a proton transfer. After the proton transfer, we get a species which looks like this specific one. Now look, again we have a positive charge on oxygen, but if you look closely you will see that this specific part here, this is nothing but water. I have just written this in an inverted way. So we all know that water is very much stable. So in this case what happens is this specific oxygen atom can now break the bond with carbon, because it now has a chance to produce something more stable, which is water. So as this is an incentive for this oxygen atom, so as a result of that this specific carbon oxygen bond is broken. And in order to help that cleavage, this specific oxygen also helps by donating its electron pairs, and thus we get a dehydration step, and we also get the reoccurring of the carbon oxygen double bond with obviously a positive charge on the carbonyl carbon. Now as we told you earlier, this specific scenario is not suitable as oxygen is having a positive charge and 3 bonds. So what this oxygen atom will now do is it will try to break one of the bonds. Now it has option to break one of the carbon oxygen double bonds, or it can break the oxygen hydrogen bond here. So energetically it is more favorable for this oxygen atom to break this OH bond rather than this carbon oxygen double bond here, and it certainly does that, and by deprotonation it gets back to its original neutral carbon oxygen double bond scenario. But look, at this stage we do not have our starting carboxylic acid, rather we have a different molecule which is known as ester. So this is the whole reaction mechanism of the esterification reaction. Now this reaction itself is present in 10th standard, but the mechanism is actually present in the 12th standard. But even if you are a 10th student, it will not hurt to learn about this mechanism, because this reaction actually has a more practical application in our daily life. I am sure you guys have heard about the molecule aspirin. Now this specific molecule aspirin is made or produced by using this specific esterification reaction. But for that esterification reaction we do not take an carboxylic acid, rather we will take an acid anhydride, and with that we react salicylic acid, which looks like this. When these two reacts together, in presence of protons or acid, we get acetyl salicylic acid. And this specific molecule is also known as aspirin. The chemical name of aspirin is acetyl salicylic acid. And this specific molecule here, it's known as salicylic acid. So this is one of the practical applications of the esterification reaction. Now, at the beginning of the reaction, I told you that this esterification reaction is a reversible one. Reversible means the products can also form the reactants back. So now let's think that, or let's assume that we have a carboxylic acid and an alcohol, and we have applied a trace amount of acid to actually give us an ester. Now ideally this ester should give us back this carboxylic acid and this alcohol, but what we do is we tend to take up the water formed during the reaction to actually prevent this backward reaction. And if we say react and base, let's say NaOH, with this ester will break and we will get back our alcohol and we will get a sodium salt of the starting carboxylic acid. Now this specific product is used in soaps, and hence the reaction of an ester with an alkali, let's say NaOH, or it can be KOH also, to form the alcohol and the sodium salt of the given carboxylic acid is known as the saponification reaction. Meaning during the esterification reaction we were taking the acid as the catalyst, but once we have the ester, if we react and base with that ester, we will get our desired product to make the soaps, and hence it is known as the saponification reaction. So these were the mechanism and the related things which we should know about the esterification and saponification reaction. Now I hope you don't have any doubt in regarding these two reactions, but if you have, kindly let me know. Okay, thank you.